Hello, everyone, and thank you for joining us today. Our today's topic is on from data to intelligent automation, building trust, AI pipelines for outcome-based BIM. My name is Manish Day. I work as the Associate Vice President with Virtual Building Studio, where we help AEC firms establish scalable delivery infrastructure and support end-to-end project workflows. From design support and drafting to BIM modeling, coordination, and product delivery, today's session explores how AI is entering BIM workflows and why building reliable AI systems require more than just algorithms. It's my pleasure to introduce our speaker, Nabil, CTO of Nacon. Nabil specializes in AI and emerging technology for the AEC sector with expertise in software development, high performance graphics, and data processing. His work focuses on applying AI to automate design workflows, improve compliance process, and enhance operational efficiency. Nabil, thank you for joining us today. Before Nabil begins, a quick note for everyone. If you have any questions during this webinar, please add them in a Q&A session, in a Q&A panel, and we can take it forward at the end of the session. Nabil, I hand it over to you. Thank you.
Thank you very much for the introduction. Hi, everyone. Good morning, afternoon, or evening, depending on where you are. And thank you again for the introduction. So let's start. You've already done, I think, a really good introduction of what I do and what we do. But just to summarize very quickly, I am myself a software developer. I specialize and have expertise in high-performance graphics, artificial intelligence, and data processing. So I've been focusing on AI for more than a decade now, and I have developed a system for the AEC industry. I'm also the co-founder of Nacorm, which is a company specializing in AI and the development of new technologies in the AEC sector. So why this presentation today? As you all know, the integration of AI into AEC is progressing, but very slowly, and it has been held back by a lot of technical obstacles. The main one being that data is often incomplete, heterogeneous, and poorly structured. There are also a lot of issues regarding traceability, versioning, validation, and most of the people do not even consider yet the legal and ethical frameworks around AI developments and advanced algorithms. And the result of all these issues, obstacles, and not aspects not be considered is that we end up with models that are not very robust and difficult to use in production. I'll start by giving you a couple of typical mistakes in AI projects, and then we'll go into how to avoid making these mistakes and how to actually build the pipeline. So we often see in projects that we work on data issues, mistakes with incomplete or mislabeled data. Failure to consider constraints, so not considering any legal constraint, for example. Governance issues, lack of traceability, versioning, or validation. This happens a lot, and with governance issues, you end up with decisions that are indefensible, not trackable, and not traceable, and unauthorized in production. And finally, you have probably the most common one, which is unreliable results. You cannot explain the results, you cannot identify the biases, and therefore you will have the users as well as the whole system rejecting your solutions and your models. So the right approach is building a fully integrated pipeline and focusing on 4 pillars or 4 aspects. The first one is data, understanding and labeling your data. The second one is AI, by identifying and understanding the different and various technologies and their applications. The third one is ethics, anticipating and reducing biases. And finally, legal, define responsibility and protect your project. Only by implementing these 4 pillars as a one complete pipeline and integrated pipeline, you can have a working AI system. So let's start with data, understanding and labeling your data. So you might ask yourself why data is the foundation of AI. Well, you've probably seen it many times. Data quality is entirely dependent on AI quality. Secondly, AEC data, as we said, is often incomplete, heterogeneous. You have data scattered all around systems. You don't have good compatibility, good interactions between the system. And finally, AI, as well as advanced algorithms, are entirely dependent on data. There are 6 main data types: numeric, text, audio, visual, or 2D data, video, and geometric, or 3D. It is very important that when you consider your data, you look at these 6 main data types. You might argue that there might be more or there might be less, but from my research, university research, as well as my various projects I've worked on, these are the main data types, and all the data you have will fit in one of these categories. So let's start with numeric data. Numeric data is information expressed as numbers for measurement or calculation, such as cost data, planning data, telemetry and sensors, and resource utilization. Numeric data is very easy to process and compute for a computer. So machines love numeric data. But the main issue is that without proper calibration or proper conversion, numeric data can mean anything. You don't have any context attached to it. So 15 can mean 15 meters, can mean 15 million. We don't really know. So it is very important to properly calibrate and properly save and convert numeric data. Then we have text data, information conveyed by sequences of characters or words, such as site reports, contract documents, standards, and project specifications. Now, text data can be any sequence of characters. So obviously you have text documents that can be understood by humans, such as emails, site reports, and all the ones we've mentioned. But you can also have sequences of characters that are very hard for humans to understand or don't really mean anything to us, but can still encode valuable information, such as, not talking about the AEC industry, but like DNA, for example. That's a sequence of character that doesn't really mean anything to us, but can encode information. Audio data is information captured as variations in sound over time, such as meeting recordings, for example, voice note, safety briefings. So you've probably all worked with all of this that data source. But you also have one that is very, very interesting and not often looked, very often overlooked, which is noise monitoring. So let's say you have a machine. A machine makes a certain noise. You know the machine needs to make this noise when it's running. And then suddenly it makes a different noise. You, as a human, you can detect this pattern. You listen to this machine every day, so you know that something is wrong and the machine is probably gonna break at some point, so you need to do predictive maintenance. It's the same thing with audio data. You can record a machine, record a noise, and then over time detect a pattern, which is classified as the normal sound and normal noise a machine is supposed to make. And then if the sound differs at some point, then you need to call maintenance and then do predictive maintenance on the machine. Then you have visual data, or 2D data. Information represented as a flat grid of pixels, such as photographs, scanned sketches, PDF plan sets, or 2D CAD drawings. Now, visual data can also encode things that are seen by humans, such as, again, photographs or images, but also encode information that is not obvious or understandable by humans, such as more advanced geometric placements or things like normal maps. So again, visual data is quite complex to process for a computer, There are different techniques, and we'll talk about these techniques when we'll talk about the AI models. Video data is, a lot of people think this is very complex, but actually much simpler than we think. It is information represented by a sequence of images played over time to represent motion. Sequence of images. Images are the 2D data that we've seen just before that. So when you play those images over time, the only piece of information that you're adding is motion. The difference between the first and the fifth frame, or the difference between the 7th and the 12th frame, this is motion. You have, for example, drone videos, progress images, site videos, or training videos. And the way you will extract information from that is by extracting the video, the image, so 2D information, and then comparing each image to detect motion difference over time. Finally, we have geometric data, or 3D data. Information defined by points or shapes in three-dimensional space, such as LiDAR scans, which creates point clouds, such as GIS models, Revit, BIM models, and similar to 2D image information, this can be used to represent visual information or encode geometric information. So now that we have these 6 data types, we need to evaluate them. And in order to evaluate them, we will look at accuracy, consistency, completeness, and accessibility. You can integrate more data quality attributes, but from my expertise and my point of view, it is unnecessary. You will just waste time and waste money when you want to focus on having a good data set that works, and then in the future you can improve the data even more. So let's start with accuracy. The data correctly reflects real-world facts or events, free of errors or distortions. Accuracy is completely different to precision. On the right, you can see a precise data set. All the dots are very, very close to each other, but they completely miss the center of the target. On the left, you have an accurate data set. Yes, the points are not very close to each other, but they're consistently around the center of the target. And this is what you want. You want an accurate data set. If you have a data set that is both accurate and precise, that's even better. But if you have to choose, all you want is accuracy. Then you have consistency, ensuring data is represented identically across systems in both value and format. So again, on the left, you have a consistent data set. The names are consistent: A01 cube, A02 beam, A03 pyramid, and the units are the same. But more importantly, the orientations are all the same. On the right, you have an inconsistent data set. The names are different, the units are different. This can be solved quite easily, but the orientations are wrong. And this is very, very hard to fix automatically. So make sure that if you're working with 3D geometric models, such as automatically placing equipment in Revit, for example, you have a data set that is consistent and where the models have the same orientation. You then have completeness. All the required data is captured with no necessary parts missing. So again, on the left, you have a complete data set. On the right, you have an incomplete data set. I think this is pretty self-explanatory. But what is important here is that we're looking at all required data. So all the data needed, necessary, is present. It's not missing. But we also don't want to have too much data. We only need required data. The extra additional data is not necessary and will just add complexity to your system and to your process. Then we have accessibility. probably the most important of these four. The ease with which authorized users can locate, retrieve, and use data when they need it. You can have the best data set, the cleanest, the most accurate, the most consistent, the most complete. If you cannot access it, it's like if you do not have any data set at all. So it's very important to make sure that it's accessible, you can access it, and you can access it quickly and when you require it. One important notion that I haven't talked about is internal versus external quality. Internal quality refers to everything within your organization systems. So you have full control over your internal data quality. External data quality is the quality of the data you interface with. So a provider information, other system information, an external database. In order to have the best interoperability and exchange between the systems, first you need to comply with industry standards or partner specifications. But more importantly, you need to make sure that every single external data that enters your system goes through your own validation. That is very important. So, to finish on this data part, this is what a typical AEC data pipeline looks like. You start with collection, where you will collect all the information from different sources. Then you will evaluate it using the 4 data attributes we just discussed. You will then structure the information in table, databases, and then you will clean your data. The cleaning only happens after collection, evaluation, and structuring. Because if you start cleaning too early, you will make it way more complex than if you do it once the data is fully structured. And finally, you have the enrichment part. So enrichment is about adding more data or more precise or more data source in a way. And again, this enrichment has to be done only on clean data. Otherwise, you just add complexity to your processing pipeline. So we just looked at data. So now we're going to switch to the AI part of our pipeline, identifying AI application. First, a quick review of algorithm versus artificial intelligence. So an algorithm follows a fixed series of steps, as you can see on diagram, step 1, step 2, then you might have a branch, but you have a fixed series of steps, like a cooking recipe. And it always behaves the same way when it's provided the same input, so it's deterministic. Artificial intelligence uses data to improve over time. So you have your data set, this will be fed into the model, and the model will learn from the data to make decisions. So the AI systems and models can adapt to new situations and make new decisions without explicit instructions, but it is not deterministic and it is very data driven. So it depends on the quality of your data, hence all the data section and data things we've discussed before. So we're going to look at a couple of AI technologies through the human abilities framework, such as the ability to see, hear and speak, understand language, act, learn, find, and finally reason. So first we have the ability to see, and this is called computer vision. So it's about interpreting images and 3D environment to extract useful information and detect patterns. You can use that, for example, to implement automated quality control. So you will have computer vision that analyze 3D BIM models and sci photos to detect deviations and ensure compliance. In that case, you will have computer vision on both the real-life construction and the BIM model. You can also have object recognition and classification, where AI identifies and classifies construction elements, door, windows, pipes, etc. You then have the ability to hear and to speak. And this is done with speech to text and text to speech. So speech to text enables voice synthesis transcription. So you go from speech and then you convert that into text. So that's transcription. Text to speech is the opposite. You take a text and you're gonna synthesize voice from this text. So text to speech. Now, you've probably used these technologies a couple of times before, and with that, you can implement a virtual BIM assistant. So with text to speech and speech to text, you'll be able to communicate and interact with the BIM model and get answers very quickly. Or you can have automated BIM model documentation. So speech to text, so taking a voice, converting into text, we'll be able to transcribe spoken notes from inspectors, from architects into BIM data. We talked about the ability to see, hear, and speak. Now we need to be able to understand language. And this is done with a technology called natural language processing. And I'm sure most of you, if not all of you, have already used that a couple of times before. So it enables interpretation, analysis, and extraction of information from text data. And this is where we can process our text data that we've seen before. We can implement, for example, automated compliance checking, where the NLP model will analyze regulations and compare them with BIM models to flag non-compliance. We can also have issue tracking and reporting. The model processes incident reports and links them to the BIM element. So everything is centralized and everything can be processed faster. We now have the ability to act, and this is done by two fields, robotics and automation. The main difference is that robotics tends to be more for physical action and physical automation in a way, and automation tends to refer more to the virtual aspect of things, so more software related. And it's about automating repetitive or complex tasks using intelligent systems and robots. So with that, we can implement, for example, automated prefabrication and assembly, where robots will use BIM data to cut, assemble, and transport components. And we can have, for example, AI-powered site inspection. So again, using drones and robots, we could navigate sites and use computer vision with robotics to compare progress to BIM models and detect real-time discrepancies. Then we have the ability to learn, and you've probably all heard about that. This is done through machine learning. So machine learning is about using historical data to identify patterns and generate predictive models, and that's very important. In terms of input data, we can use pretty much anything that is useful and related to the problem we're trying to solve. And with that, we can implement construction risk assessment, where we will analyze historical data and BIM models to predict delays, cost overruns, and so on. Or we can have AI-based cost estimation. Similarly, we will analyze previous BIM models, previous projects, and previous cost projects to be able to predictively estimate the budget and reduce uncertainty. Find, the ability to find, is something that is used more and more, and it's done for a technology called retrieval augmented generation, or RAG. So you've probably all heard about RAG before. And it combines information retrieval and context generation to deliver accurate contextual responses. The most important part here is the contextual response. We care about the context, the request context, the prompt context, and we care about the search context. And with that, we can, for example, implement automated specification matching, where the model compares manufacturer databases with BIM requirements to recommend optimal materials. We can also have smart issue resolution, where AI will analyze past issues and suggest contextual solutions within the BIM environment. So again, what matters for RAG models is the context. It's not just a normal classic search engine like you would have on the previous version of Google, for example. It doesn't only look at keywords, it looks at the search context, and it looks at the database context. Finally, and probably the most advanced one, is the ability to reason. And this is done through logical inference. So it applies logical rules to make informed decisions based on available data. The important part here is making a decision based on available data. We typically will not have a perfect solution, but the model, based on the data provided, will give the best solution it can find. And with that, we can, for example, implement design conflict resolution, where AI analyzes conflicting requirements, such as having structural and energy efficiency requirements that conflict, and suggest optimal solutions. So we will suggest, again, the optimal solution because there is no single perfect solution. We can also have layout optimization, where the model recommends optimal spatial layouts based on functional and regulatory requirements. And again, when it comes to layout optimization, there is not one single perfect solution. So it will take all the data and make a decision, the best decision it can make, and provide that to the user. But again, that's not the perfect solution because there is no perfect solution. We looked at data, we looked at AI, and now we're going to look at the ethics side of things. So the ethics and legal side of things, I'm going to approach them from a technical perspective. What matters is not the philosophical discussion behind it, but it's more about how do you consider them when you build your system, or when you have a developer, or when you purchase a system, or you have a partner developing a system for you. So how do you consider that, and making sure that you don't have any ethics or legal issues in the system you're going to use. So ethics. Why is it important? First of all, AI systems reflect human choices, data, goals, assumptions. And uncontrolled AI bring risks of biases, exclusion, and harm. So ethics is not just, again, a philosophical value, it's a practical design constraint. So let's have a look at a couple of cognitive biases first, and then logical errors. Starting with, for example, the ostrich effect. The ostrich effect is willfully ignoring disturbing or uncomfortable information. This happens very, very often in LLM models, such as the OpenAI models, Google models, Claude models, and it's a bias that is very present. So when you build your system, or when you evaluate a provider system or a developer system, or doesn't matter, always ask yourself, will this bias happen in this system? You can have, for example, anchoring bias or framing effect. Let's talk about framing effect. Framing effect is being influenced by the way information is presented. Again, this is very present with LLMs, such as ChatGPT, because the first information you will provide will direct the rest of the conversation. So again, this is very present, so you need to be careful. We have logical errors, which are different from cognitive biases. So logical errors are usually split into 4 parts. You have the attack and diversion errors, appeal to emotion, appeal to authority, and error in logical reasoning. So let's look at biased sample, for example, the last card. Evidence based on non-representative sample. So this ties directly with the data part we've discussed before. If your data set is too small, or if your data set is not broad enough or doesn't cover enough cases, you will end up with a non-representative sample. So everything your AI models or advanced algorithm will produce will either be wrong or biased. So again, these cognitive biases and logical errors are just a sample of what you can find. The idea is to try to ask yourself if sample if a system has this bias or this logical errors as much as you can in order to reduce them and reduce the errors and the mistakes that end up from using this model. Finally, the last part, legal. Define responsibility and protect your project. So, again, why legal framing is essential in AI projects. AI results can affect real-world design. And again, without a legal framework, no one knows who is responsible. So, similar to ethics, legal isn't about restrictions, it's about clarity, protection, and it should be used as a framework to structure and develop your system and not a constraint. So, I'm first going to give you a couple of legal risks in AI projects, and then I'll give you some hints and pointers on how to reduce these risks. The first one is lack of ownership. So who owns the model, who owns the data, and so on. Secondly is no versioning. We cannot prove what was used, so we cannot backtrack the results and trace what has been happening in the model. Then we have no audit trail. Cannot justify the model choices, which links directly with versioning. Lack of approval, so unauthorized use in production. And finally, misuse. So using a model or a system that is designed to do a first task to do a completely different task. And this can lead to reputational damage or lost contracts. So how do we define responsibility? So first of all, we need to define it from the beginning. Who owns the data? Who owns the model? And who owns the decision? That's the three questions I need to ask yourself. Secondly, you need to assign roles. You have the vendor, the integrator, the validator, and the user. This will help you define who owns the data, the model, and the decision, and the responsibility in general. Thirdly, involve legal departments and project management from the start. Even if you're not a big company with a big legal department, or you don't even have a legal department, that's fine. But you should still consider the legal aspect of the model and the system you're building or you're going to use. Finally, add human checks when results matter. Don't add human verification at every single step, otherwise you don't have an automated model anymore. Add it when results truly matter. So let's have a look at three main categories of risk assessments. You have the business risks, so you're probably all very familiar with that, such as like cost overrun, for example. You have the data risks, ownership or access conflicts. So who owns the data, who can control the data, who is allowed to use the data. And then you have the artificial intelligence risks, such as lack of human oversight, or maybe a model being deprecated, or a model giving wrong responses. So that's a risk as well. So you have three examples here, one for each category, but obviously there are many more. The goal is to challenge the system, challenge the pipeline, challenge the architecture, and the risk won't magically disappear, but it will help you to, one, be aware of the risks, and two, mitigate them if possible. So, in conclusion, how to go from these principles to practice. We've discussed 4 parts, 4 pillars. Do not skip any of them. You need to have high quality data, rigorous AI implementation, and knowing what each model does, proactive bias management, and clear legal framework. You need to use the proper model for the proper tasks. Don't use a hammer to screw, for example. You need a hammer for a nail, a screwdriver for a screw. That's the same thing with AI. And ignoring even one of these pillars weakens the entire system and will lead to failure. So the goal is to have models that are traceable, explainable, and usable in real world. Thank you very much for listening to me. If you have any question, feel free to ask.
Thank you, Nabil. For such insightful wonderful session. To all the attendees, if there's any question, you can put it in the chat box, or we always share Naveed's credentials. You can, get in touch with him directly. But if you have any questions right now, we are more than happy to answer it. So, anyone? So, Nabil, there's a question on LinkedIn by Bill Torres. Well, the copy of this presentation will be shared afterwards.
Yes, of course. Yeah.
Yeah. So, yeah. Cool. What else? So, what we do is, we'll conclude this session. I think people will reach out to you directly if required. But thank you, Nabil, for sharing the insight, and thank you everyone for joining us for today. We hope this session helped you better understand how trusted data governance, responsible implementation are essential for building effective AI and BIM workflow. There is someone recording something. Let me wait for some time. Okay, I think Sienna Mia. I think we will we'll touch base with you. It's just halfway through, like it says recording. I think that's Sienna, do you want to be specific so we can, Nabil can answer it? Anyways, so I think it just conclude this session. Thank you so much, Nabil. We will end it. Thank you so much, Ian, and thank you so much, everyone. We'll share the credentials. You can get in touch with Nabil directly if you have any questions or if any query if required. Thank you.
Thank you very much. Thank you, everyone.
Take care, guys. Thank you, Ian.